What if the darkest part of space is not empty at all? What if two dying machines have just shown us that the silence beyond our solar system is hotter, harsher, and stranger than we ever imagined? And before we go 1 inch farther into the dark, tap like, subscribe, and share this video with one person who still feels awe when they look up at the night sky. Right now, while most people are sleeping, working, driving, scrolling, or worrying about things here on Earth, two spacecraft built in the 1970s are still moving through a place no human being has ever touched. They are not near Mars. They are not near Pluto. They are beyond the giant bubble made by our sun. They are out in interstellar space, the region between the stars. And even now, nearly half a century after launch, Voyager 1 and Voyager 2 are still sending messages home. That fact alone should stop you for a second. These machines were never supposed to live this long. They were built for a much shorter mission. They were meant to visit the outer planets, make history, and slowly fade away. Instead, they kept going, year after year, decade after decade. They outlived presidents, computers, generations of engineers, and the world that created them. And now, in 2026, they are doing something even more unbelievable. They are rewriting what we thought we knew about the border of our solar system and the space beyond it. NASA has confirmed that Voyager 1 had to shut down yet another science instrument in April 2026 just to stay alive. That is how fragile the mission has become. Engineers are dealing with a spacecraft so far away that a signal takes almost a full day to reach it. They are working with hardware from another era. They are managing power levels so low that every single watt matters. One bad drop in power could force the spacecraft into a protection mode that might be hard to recover from. And yet, even in that weakened state, Voyager is still giving us data that feels almost unsettling. Because the big discovery is not some alien signal. It is not a giant object hiding in the dark. In a way, what Voyager found is more disturbing than that. It found that the space outside the sun's protective bubble is not calm, not empty, and not behaving the way many people expected. It is more intense, more energetic, more compressed, more alive with invisible activity than our old picture suggested. That matters more than it may sound, because for most of human history, we looked at the night sky and imagined the space between stars as a silent void, cold, black, and empty. But Voyager has shown us that the edge of our cosmic neighborhood is more like a battlefield than a blank page, a place where the solar wind from our sun presses outward, while the interstellar medium pushes back. A place with heated plasma, strong radiation, changing particle density, and a constant electromagnetic hum moving through the dark. And the deeper Voyager goes, the stranger the story becomes. To feel how incredible this is, we need to go back. In 1977, NASA launched Voyager 1 and Voyager 2 because of a rare alignment of the outer planets. That alignment created an opportunity that happens only once in many lifetimes. By using gravity from one planet after another, the spacecraft could travel much farther than normal. It was like finding a perfect series of moving stepping stones across the solar system. Voyager 1 launched in September 1977. Voyager 2 launched a little earlier, in August. The names sound backward, but that is because Voyager 1 took a faster path and reached Jupiter and Saturn first. Voyager 2 went on the grander tour. It visited Jupiter, Saturn, Uranus, and Neptune. It gave humanity our first close views of worlds that had only been distant mysteries. Think about how bold that mission was. These spacecraft were launched before the internet, before smartphones, before most homes had personal computers. Their memory was tiny by modern standards. Their processing power was weak compared with even cheap devices today. And still, they crossed the solar system and transformed our understanding of the outer planets. Voyager 1 showed us the violent beauty of Jupiter and its moons. It revealed active volcanoes on Io, the first volcanoes ever seen beyond Earth. It gave us stunning looks at Saturn and Titan. Voyager 2 then went farther, becoming the first and only spacecraft to fly past Uranus and Neptune. Without Voyager, those worlds would still be much more mysterious than they are now. That alone would have made the mission legendary. But then came the part no one truly expected. After the planetary flybys were done, both spacecraft kept flying outward. NASA did not turn them around. There was nowhere to turn them. They were sent toward the edge of the sun's domain, past the planets, past the Kuiper Belt region, toward the invisible boundary where the influence of our star weakens and interstellar space begins. That boundary is tied to something called the heliosphere. The heliosphere is like a giant protective bubble made by the sun. The sun constantly sends out a stream of charged particles called the solar wind. That wind rushes outward in every direction and carries the sun's magnetic field with it. Together, they create a huge bubble around the solar system. Inside that bubble, we live under the partial protection of our star. Outside it, conditions are different, much different. Inside the heliosphere, the sun helps shield us from part of the galaxy's high-energy radiation. Outside it, that shielding drops. Inside it, the environment is shaped mostly by the solar wind. Outside it, the interstellar medium takes over. That is the thin gas, plasma, dust, and magnetic field spread through the space between stars. For years, scientists could model this boundary. They could estimate it, they could debate it, but they could not directly touch it. Voyager could. Voyager 1 crossed into interstellar space in 2012. Voyager 2 crossed in 2018. Those moments were historic. For the first time, human-built objects were not just looking at the edge of the heliosphere from far away. They were passing through it and taking measurements from inside the environment itself. And what they found was not a simple clean border. It was messy. It was uneven. It was more extreme than many people imagined. Even before we get to the newer discoveries, that alone is fascinating. The edge of our solar system is not like a neat shell around a toy globe. It is more like a shifting frontier under pressure. The sun pushes outward. Interstellar space pushes inward. Magnetic fields bend and twist. Charged particles pile up. Conditions change depending on time, place, and solar activity. Now add one more layer to the story. As of 2026, Voyager 1 is more than 15 billion miles from Earth. Voyager 2 is more than 13 billion miles away. These numbers are so huge that they barely feel real. So try imagining it another way. Light from the sun reaches Earth in about 8 minutes. A radio signal from Voyager 1, traveling at light speed, takes almost 24 hours to get here. That means when NASA sends a command to Voyager 1, the team cannot see the result right away. They wait nearly a full day for the spacecraft to receive it. Then they wait again for a response to come back. A simple test can stretch across 2 days. A mistake is slow. A fix is slow. Everything is slow. And still, the spacecraft keep whispering across that impossible distance, but keeping them alive is getting harder. Voyager does not run on solar panels. It is too far from the sun for that. Instead, each spacecraft uses a radioisotope thermoelectric generator. In simple terms, it turns heat from decaying plutonium into electricity. It is one of the great engineering decisions in space history. Without that power source, Voyager would have died long ago. But there is a limit. Every year the spacecraft lose a little more power. NASA says the probes lose about 4 watts per year. That may not sound dramatic. In your house, 4 watts feels tiny. But for Voyager, that is precious life leaking away. When your total power budget is already painfully small, losing a few watts can mean losing an instrument, a heater, or eventually the ability to keep the spacecraft stable and awake. So engineers have had to make sacrifices. Over the years, they turned off cameras. They shut down systems that were no longer essential. They kept only the most valuable science running. By 2026, Voyager 1 is down to just 2 operating science instruments, the plasma wave subsystem and the magnetometer. Voyager 2 still has 3 active science instruments, but its future is just as delicate. Then came the warning sign. On February 27, 2026, during a planned roll maneuver, Voyager 1 had an unexpected drop in power. That got everyone's attention. Why? Because if power fell too far, the spacecraft could trigger its undervoltage fault protection system. That is basically a self-defense mode. It would begin shutting down components automatically to protect itself. That may sound helpful, but on a spacecraft this old and this far away, any automatic shutdown creates risk. Recovery is slow. Recovery is uncertain. Recovery uses time and trust that the spacecraft will still respond the way engineers hope. NASA did not want to wait for that to happen. So on April 17, 2026, the team sent commands to turn off the low-energy charged particles instrument, known as LECP, on Voyager 1. This was not because the instrument had failed. It was still working. It had been operating for nearly 49 years, but NASA needed to save power and reduce the chance of a deeper problem. Shutting it down bought about a year of breathing room. That one sentence says everything about where Voyager is now. A spacecraft that helped change planetary science is now living year to year on borrowed power. And yet, the story does not become less amazing there. It becomes more dramatic. Because NASA is now preparing an engineering move with a nickname that sounds almost too intense to be real. The Big Bang. That is the informal name for a plan to switch off some powered devices and replace them with lower power alternatives all at once to squeeze more life out of both Voyagers. The idea is simple in theory and nerve-wracking in practice. Reorganize the power system, free up energy, keep the surviving instruments alive longer, maybe even long enough to keep sending science into the 2030s. If this story is already pulling you in, hit like, subscribe, and share it now, because the deeper we go, the more unbelievable this mission becomes. The Big Bang matters because Voyager is still in a one-of-a-kind place. No other active spacecraft is out there doing what it does. Telescopes can look at distant stars. Space probes can study planets. But Voyager is physically inside the medium beyond the heliosphere, measuring it from within. That is rare beyond words. It is like the difference between looking at a storm on radar and standing inside the storm with sensors in your hand. So what exactly is Voyager discovering that has people paying such close attention? The first part of the answer is the nature of the boundary itself. For a long time, many people pictured the edge of the sun's influence as something simple. Maybe not a hard wall, but at least a smoother transition than what Voyager found. Instead, the crossings by Voyager 1 and Voyager 2 showed that the heliopause, the boundary between the heliosphere and interstellar space, is complex. It behaves differently in different places. It changes with conditions. It can show turbulence, compression, particle jumps, and layered structure. That means our solar system is not traveling through the galaxy wrapped in a perfect sphere. It is moving through a medium that pushes back. And that pressure from outside matters. One clue came from temperature. When Voyager 2 crossed the boundary, NASA reported that the plasma outside the heliosphere was slightly warmer than expected. That might sound technical, but it is important. Models are useful because they give us a picture of what should happen. When reality shows something warmer, denser, stronger, or stranger than the model predicts, it means the story outside our solar bubble is more dynamic than we thought. And then there is density. This may be the most haunting part of all. As Voyager 1 moved farther into interstellar space, scientists found that the electron density around it did not stay flat. According to NASA, it began rising after 2013 and reached much higher levels by the middle of 2015, about 40 times higher than the earlier baseline just outside the heliosphere. Stop and let that sink in. Voyager went farther away from the sun, yet the local plasma environment around it became much denser than expected. Why? Scientists have ideas, but not a final answer. One idea is that interstellar particles slow down near the heliopause and begin to pile up, almost like traffic on a highway approaching a choke point. Another idea is that the interstellar magnetic field compresses material in a way that creates lower density and higher density regions. And Voyager is moving into one of those denser zones. Either way, the message is clear. The space beyond our solar bubble is not just an empty drift. It has structure. It has variation. It has hidden architecture. And that is what makes the discovery feel so eerie. The more we measure, the less empty the dark becomes. Then comes the part people often describe as the hum. Now, space does not carry sound the way air does on Earth. If you were floating in a vacuum, you would not hear a normal sound wave moving through it. But plasma, the charged gas that exists throughout space, can support wave behavior. Voyager 1's plasma wave instrument detected a persistent signal in interstellar space, not just brief bursts linked to solar events, but a steady emission that gave scientists a way to track density more continuously. That changed everything. Before that, researchers relied heavily on sudden plasma oscillations caused by shock waves from the sun. Those bursts were useful, but they were temporary. The new signal was different. It offered a more ongoing way to probe the local interstellar medium around Voyager. Imagine sitting in a dark room and seeing only rare flashes of light. Then suddenly, a dim lamp turns on and stays on. You still do not see everything, but the room becomes far less mysterious than it was moments earlier. That is what this persistent plasma signal did for scientists studying interstellar space. And emotionally, it hits hard, because it means interstellar space is not just a silent black backdrop. It has a kind of activity, a texture, a behavior, a measurable vibration moving through it. The oldest surviving spacecraft from Earth is out there listening to the medium between stars and finding that it is not still, not quiet, not simple. Then we get to radiation. Inside the heliosphere, the sun helps protect us from part of the galaxy's cosmic rays. It is not perfect protection, but it matters. When Voyager 1 crossed into interstellar space, its instruments recorded a sharp change in cosmic ray levels. That told us directly that once you step outside the sun's protective bubble, you enter a harsher radiation environment. That is terrifying in a very real sense. Not movie terrifying, not monster terrifying. Physics terrifying? The kind of terrifying that matters if humanity ever dreams of deep interstellar travel. We are used to thinking of space as empty distance, but distance is not the only problem. Environment is the problem. Radiation is the problem. Energy is the problem. Power is the problem. Navigation is the problem. And Voyager is showing us, in direct measurements, how severe that environment really is. If you want to send human beings, or even advanced machines, into the space beyond the heliosphere for very long journeys, you are not just crossing emptiness. You are entering a region that is more exposed, more energetic, and less forgiving than our solar neighborhood. Voyager is not only exploring that truth, it is warning us about it. And then there is the magnetic field. The interstellar magnetic field near the heliosphere has turned out to be important enough to reshape how scientists think about the boundary around our solar system. The field pressing in from outside appears strong enough to help control the size and shape of the heliosphere more than many expected. That helps explain another surprise. Scientists once thought the heliosphere might swell a lot during periods of stronger solar activity and shrink more during quieter periods. But when Voyager 1 and Voyager 2 crossed years apart during different phases of the sun's cycle, the overall boundary distance was not wildly different. That suggested the outside pressure from interstellar space was stronger and more influential than many old models assumed. In plain English, our solar system's protective bubble is not free to expand however it wants. The galaxy squeezes back. That idea is beautiful and unsettling at the same time. Quick pause before we go deeper. If you love space stories that feel bigger than science fiction because they are real, subscribe right now. Leave a like and share this video with someone who needs a reminder that the universe is still full of shocks. Now think about what that means on a human level. Everything you have ever known has happened deep inside this protective bubble. Every war, every love story, every invention, every poem, every child born, every city built, every song ever sung on Earth happened under the influence of the sun's shield. We do not usually feel that shield. We do not wake up thinking about it. But Voyager makes that invisible protection invisible by stepping outside it. Only after leaving the shield can you truly measure what the shield was doing for you. That is one reason the mission feels emotional, not just scientific. Voyager reveals the outline of home by leaving home, and the farther it gets, the more precious that home begins to feel. And still, each command matters. That is why the recent power crisis feels so intense. When NASA shut down the LECP on Voyager 1, it was not just a routine update. It was a reminder that even legendary missions are mortal. Every active instrument left on Voyager is now something like a heartbeat. Every year of extra life is a small miracle created by engineering, discipline, and luck. But the mission's weakness is also part of its power. There is poetry in that. Voyager had cameras once. It showed us moons, clouds, rings, storms, and giant worlds. Those cameras were turned off long ago because there was nothing left to photograph in the normal sense. Interstellar space is too dark, too empty of bright nearby targets, too demanding on power. So now Voyager does a different kind of seeing. It listens to plasma waves. It senses magnetic fields. It measures charged particles. It reads the invisible instead of the visible. That is not a smaller achievement. It may be an even bigger one. Let's deal with one important question. Why call this discovery terrifying at all? That matters for science. It matters for future missions. And the story becomes even more striking when you compare Voyager 1 and Voyager 2 directly. These spacecraft did not leave the heliosphere in the same direction. They crossed in different places and at different times. That means they sampled the boundary from different angles. And their experiences were not identical. That alone tells us the heliopause is not uniform. It is not the same everywhere. Conditions can vary depending on where you cross. That is like discovering that the walls of your house change shape and temperature depending on which room you stand in and what season it is. It means the edge of the solar system is more complicated than a single clean line on a diagram. This is one reason scientists are so interested in combining Voyager data with newer missions, such as IMAP, the Interstellar Mapping and Acceleration Probe. IMAP is designed to study the heliosphere and help build a better large-scale picture of how our solar system interacts with the interstellar medium. Voyager gives us direct local measurements from out there. IMAP helps map the broader structure from closer in. Together, they can sharpen the picture. And what picture is emerging? A solar system moving through the galaxy inside an asymmetric, pressured, dynamic bubble. A bubble shaped not just by the sun's output, but by outside magnetic fields and the local interstellar environment. A frontier that is not smooth, a region where density can rise unexpectedly, a place where plasma waves provide a constant signal, a place where radiation intensifies once the sun's shielding falls away. That is the terrifying new discovery in its truest form. Not one single dramatic object, a whole environment that is stranger than the old simple version. And perhaps the scariest part is this. We know this only because Voyager happened to survive long enough to tell us. If the spacecraft had failed earlier, our picture would still be weaker, flatter, and more wrong. That should make you wonder what else is still hidden out there, waiting for the first instrument brave enough to drift through it. Now think about the timing. Voyager is making these discoveries at the weakest stage of its life. Many of its instruments are already silent. Power is low, risk is high, communication is slow. Yet the surviving tools happen to be exactly the ones most useful for understanding the interstellar medium. The plasma wave subsystem and the magnetometer are not flashy instruments. They do not take beautiful pictures that go viral in seconds, but they are perfect for reading the invisible conditions around the spacecraft. In a strange way, Voyager's final act may be its most profound. Not because the spacecraft is stronger than before, but because it is finally in the one place only it can study. That gives the mission a feeling almost like destiny. It launched to visit giant planets. It lived long enough to become humanity's messenger from interstellar space. It lost many tools, but kept the ones needed to answer questions nobody could fully ask in 1977. That is extraordinary. And it is also a lesson in patience. Modern culture wants instant breakthroughs, instant headlines, instant answers. Voyager offers the opposite. It is slow science in the deepest sense. It took decades to get there, decades more to gather enough context, decades of careful analysis to understand what the signals mean. This is discovery stretched across generations. Some of the people who first welcomed Voyager's launch are no longer here to see what it is finding now, but their work is still moving through the dark, still returning meaning to the world they left behind. That is one of the most beautiful things human beings have ever done, and maybe one of the saddest, too, because a day will come when the signal ends. Not because Voyager crashed, not because someone destroyed it, but because the power will finally become too little. One instrument after another will go dark, then the transmitter will fail to stay alive, then the spacecraft will no longer be able to speak. Voyager will keep drifting long after that. It may survive physically for ages, silent and cold, carrying its golden record into the cosmic dark. But its conversation with Earth will end. We are living in the last chapter of that conversation right now. That is part of why every new discovery feels so important. There will not be infinite chances. The data coming back now is part of a closing window. The Big Bang power-saving strategy may extend that window. It may even push operations into the 2030s. But nobody thinks Voyager has forever. So this is not just exploration. It is farewell science. Science gathered while the lights slowly dim. And somehow, that makes the discoveries feel even more intense. Because the spacecraft is telling us, with its remaining strength, that the galaxy outside our home is more active, more structured, and more dangerous than we once pictured. That is a message worth listening to. If this mission blows your mind as much as it blows mine, take 3 seconds now. Like the video, subscribe for more stories from the edge of reality, and share it so more people understand what Voyager is still teaching us. Let's go even deeper. A lot of people hear about interstellar space and imagine complete emptiness, but emptiness is relative. Even a very thin medium can matter when the distances are huge and the particles are energetic. Tiny changes in density, temperature, or magnetic pressure can reshape enormous structures over astronomical scales. That is why Voyager's measurements matter so much. They are not just local facts. They are clues to much larger forces. For example, when researchers saw the rise in electron density around Voyager 1, they were not just learning something about one point in space. They were learning something about how the heliosphere interacts with the surrounding galaxy. If particles pile up near the heliopause, that tells us the boundary is more active. If the magnetic field helps create compressed regions, that tells us the outside environment is not passive. It shapes the edge of our system. That has ripple effects for everything from cosmic ray transport to long-term models of our local galactic neighborhood. And this is where the story becomes bigger than Voyager itself. And here is something else worth saying clearly. Voyager did not make these discoveries by rushing. It made them by enduring. And there is a difference. That is not automatic. That is a choice. Now picture the scene that is coming in late 2026. Voyager 1 is expected to reach the milestone of being one light day from Earth. One full day for a signal to cross that gulf. That is an almost poetic number. A light minute still feels connected. A light hour feels vast. A full light day feels mythic. It means humanity's most distant machine will be so far away that its conversation with us always arrives from yesterday. Think about that. Every signal is a ghost of the day before. Every command is an act of faith sent into the future. No wonder the mission feels almost emotional to people who follow it closely. That should excite us. But it should also humble us. Because if our own solar system's boundary can still surprise us after all our progress, imagine how much of the galaxy remains misunderstood. Imagine how many neat textbook diagrams are still only approximations. Imagine how many invisible structures are waiting for direct contact before we can know them properly. Voyager reminds us that the universe is still under no obligation to match our first draft. And that may be the most thrilling part of all. Still, there's a darker side to that thrill. The harsher truth about interstellar space means future exploration will be even more demanding than the romantic version suggests. It is not enough to build a fast ship. You need radiation protection, you need extreme reliability, you need power that lasts for decades, you need autonomy, you need systems that can survive in a place where repair is impossible and communication delays are huge. Voyager gives us a preview of that challenge. It is a small, brave object facing big and different conditions. And the conditions are winning slowly. That is what the April 2026 shutdown reminded everyone. Even as Voyager reveals more, it is losing strength. Every discovery comes with a cost. Every extra year of science has to be bought with sacrifice. Instruments fall silent, so the mission can continue just a little longer. There is something deeply human about that trade. You let go of what you can to protect what matters most. That is what the engineers are doing now. They are keeping the plasma wave subsystem alive because it is still reading the local medium. They are keeping the magnetometer alive because the magnetic field still matters. They are trying to keep Voyager stable, warm enough, and responsive. They are spending power like people carrying the last cups of water across a desert. And if the Big Bang strategy works, it will be one more triumph of human ingenuity over distance and decay. Not a permanent triumph, but a meaningful one. Because a few extra years in interstellar space could mean more data on changing density, more measurements of the local magnetic field, and more insight into how the heliosphere interacts with the medium. It offers more clues about where the next generation of models is still wrong. That is worth fighting for. One last favor before we cross the final stretch. If Voyager's journey deserves more attention than it gets, subscribe, tap like, and share this video so this story travels farther than the headlines ever do. Now let's bring all of this together. The title says NASA confirmed Voyager's terrifying new discovery in space. So what is the honest version of that claim? Here it is. NASA has confirmed through Voyager's measurements and recent mission updates that interstellar space near the edge of our solar system is not a quiet, empty nothing. Voyager has shown a more complicated reality, a boundary shaped by pressure from outside and inside, plasma that is warmer than expected in key regions, and particle density that can rise sharply. It found a persistent plasma signal that lets scientists probe the local interstellar medium more continuously, in a harsh radiation environment beyond the sun's protective shield. At the same time, NASA has confirmed that Voyager 1 is now so low on power that instruments must be shut down to preserve the mission. This is happening even while the spacecraft continues to return valuable data from no other place humanity has reached. That is the real story, and honestly, it does not need exaggeration. It is already astonishing, maybe even more astonishing because it is true. A machine built when disco was still new is now beyond the heliosphere, telling us that the dark between stars has structure, motion, pressure, and a kind of hidden song. It is telling us that the cosmic ocean around our solar home is rougher than we guessed. It is telling us that the bubble around us is under pressure from the galaxy itself. It is telling us that outside our familiar neighborhood, the rules feel less gentle. That is terrifying if you thought space was just empty stillness, but it is also beautiful, because it means the universe is richer than the simple version. Richer in mystery, richer in danger, richer in truth, and yet somehow we measured it, with two machines built by human hands, with patience, with courage, with engineering, with time. One day, Voyager will go silent. The last instrument will switch off. The last signal will fade into the static. The spacecraft will continue on its endless journey. It will carry its golden record through the galaxy long after Earth's current age has become history. It will pass through darkness we will never see. It will remain a monument to a species that wanted to know what was out there badly enough to send part of itself into the unknown. But for now, the signal is still alive. For now, Voyager is still speaking. For now, we still have a voice in interstellar space. And that voice is telling us something unforgettable. Home is not the whole story. The shield around us is real. The dark beyond it is harsher than we imagined. And the deeper we listen, the less empty the universe becomes. So the next time you look up at the night sky, remember this. Far beyond the planets, far beyond Pluto, far beyond the comfortable map in your mind. A tiny aging spacecraft is still moving through the black, still listening, still measuring, still surviving, still teaching us that the scariest discoveries are not always the loudest ones. Sometimes the most terrifying discovery is simply learning that the silence was never truly silent at all.